When we're given the graph of a function, we can use what's called the horizontal line test to determine whether or not that function is one-to-one. Let's recall that if we're given the graph of a function, we can use the vertical line test to see if this graph is actually a function. If vertical lines intersect our graph at no more than one place throughout the domain, then we say, yes, this is a function. A function is one-to-one if its inverse is also a function. And to find the inverse of a function, we'll switch all the x and y values. And when we do that, it would actually cause this graph to flip or be reflected over the line y is equal to x. When we do that and we pass the vertical line test over this inverse relationship, we see that the inverse is not a function, which means therefore the original function was not what we call one-to-one. So the vertical line test is what we use to determine whether or not something is a function. The horizontal line test enables us to stay in the original function and test to see whether the original was one-to-one. If we do a vertical line test on the original, that tells us that the graph is a function. But if we pass a horizontal line test over the original, that tells us that the inverse is not going to be a function. Basically, the horizontal line test on the original yields the same result as the vertical line test on the inverse. If the original passes the horizontal line test, that would be one-to-one. If not, the original is not one-to-one. So let's look at an example of a function g of x that is x squared plus 2, but there's a domain restriction on this graph. X squared plus 2 is a parabola that's opening up, shifted up 2 units. But if we're only going to consider the x values that are positive, that would mean that we're only going to be looking at the graph in this region. So we'll erase all the ordered pairs that have negative x values, and this is the graph of our g of x function, essentially half of this parabola. In order to get the graph of g inverse, we're going to need to switch the x and the y values. So let's grab a couple of ordered pairs. So the point 0, 2 is going to correspond to the ordered pair 2, 0 on the inverse. The ordered pair 1, 3 corresponds to the point 3, 1 on the inverse. And when we graph the inverse, essentially we're taking the original graph and reflecting it about the line y is equal to x. We are switching all the x's and the y values, and so essentially we're replacing y's with x's and replacing x with y's. That's going to be a reflection about the line y is equal to x. And that's important because the graph of g inverse needs to look similar to the graph of g. If we take half of a parabola and reflect it over the line y is equal to x, the graph of the inverse should also be half of a parabola, just having been reflected. Let's notice that the graph of g is, yes, a function because it passes the vertical line test, but it's also a one-to-one function because it passes the horizontal line test. A one-to-one function is a function whose inverse is also a function. Notice over here on g inverse is a function as well, which tells us that the original must have been one-to-one. Now the horizontal line test gives us a shortcut for determining whether or not a function is one-to-one. It enables us to just work with the original. Using the horizontal line test, we can tell that the inverse is going to be a function without actually having to graph it. Let's make a note of the domain of g. With this domain restriction, the domain of g is now 0 to positive infinity. And based on the graph, we can see that the range of g is from 2 to positive infinity, including both the 0 and the 2 because this point is part of that collection. Notice looking at the graph of g inverse that the domain starts at the element 2 and goes off to positive infinity, and the range starts at the y value 0 and goes off to positive infinity. And here again we want to draw your attention to the fact that the domain of the original function is equal to the range of the inverse, and the range of the original function is equal to the domain of the inverse.